Our final lesson in Chapter 10 is 10.6, Construct and Interpret Binomial Distribution. This formula we use combinations and binomial expansion as a way to determine or calculate the probability of an event. Now, if you're working with a binomial experiment, that means you not only have one event, but you're going to have n number of independent trials. Technically, there will only be two outcomes, success or failure. The success comes from not necessarily being 50-50, but maybe based on experimental probability. So you're looking at what's happened in the past to help predict your success in the future. The failure would be 1 minus that, or the complement. So we'll have to do a little bit of calculating to use that formula down below. The formula that you're going to want to know for the binomial experiment for probability of k number of successes. Maybe, for example, you shoot a free throw 10 times. What's the probability that k would be 7? So you make 7 of them. NCK is going to stand for the fact that it doesn't matter what order you make those free throws or those successes. P is the probability you make that. 1 minus P would be the complement. So K is how many times that you'd make the shot, and N minus K would be how many times you miss. To quickly review those terms again, N is the total number of trials that you're attempting. K is how many times you want to be successful. P is the probability of that success, and 1 minus P simply means the complement of that success. We'll have to determine some of these values when we're reading and interpreting a binomial distribution problem. According to a survey, about 41% of all households in the United States have a soccer ball. Suppose you ask 6 randomly chosen households whether or not they have a ball. Determine the probability of the following events. In the given information, we should always be able to determine these key features. We should know what N equals, and that would be how many houses we're surveying. N would equal 6. We should know the probability of being successful, and in this case, if according to a survey, 41% of households say they have one, our probability would be 0.41 based on that 41%. And then the complement to that, 1 minus P, we literally just subtract. 1 minus 0.41 is 0.59. That information should all come from the given information. And if you're asked to do multiple probability experiments, that means your K value should be unique each time. For question A, it says exactly 2 houses have a ball. That means K equals 2, and that's how you know that. That's the number of successes you would want. Plugging all of this information into that formula up above, we would start off with 6C2 times the probability that you'd be successful, which is 0.41, and we want to have exactly 2 houses say they have a ball. Then times the probability of the complement to that, and that would be 6 minus 2, which is 4. And you literally just plug this all into your calculator at once. So please grab a calculator and see if you can make this work. 6C2 times 0.41 squared times 0.59 to the 4th power. Enter that in, and you should get approximately 0.3055. And that means it's about a 30.55% chance that exactly 2 houses you randomly survey would say, yep, we have a soccer ball. Now, unique wording can alter what your K value would equal. In example B, what's the probability that at least 5 houses have a soccer ball? That means K has more than one option. At least five means you could have exactly 5, or we could have 6. And then we have to think about what or means to add. So that's going to be incorporated in our work. And I'm going to need a little bit more space to write this straight across. So I'm just going to move this over right away. Let's just do one at a time. If K equals 5, the probability that just that event would happen would be 6C5 times 0.41 to the 5th power, because we want 5 houses to have a soccer ball, times 0.59 to the 6 minus 5, or the 1st power. And that would be the probability that exactly 5 houses say, yep, we have a soccer ball. But then there's or, and or means we're going to add. What if all 6 houses say, yep, we have one? That would be 6C6 times 0.41 to the 6th power times 0.59, well, that's a 9 there. If we do 6 minus 6, that's 0. Again, type all of that in at once. Pause the video and actually attempt that. Once you think you have it, press play. We just want to make sure we can do this independently. You should have 0.0458, which only means about a 4.58% chance that at least 5 houses would say they have a soccer ball. Now, that should seem likely because the probability that any one random house would have a ball is only 41%. So the likeliness that 5 or 6 out of 6 houses selected should be pretty small. All right, now it's your turn. At most, 2 houses have a ball. What does at most mean K could equal? Well, it could equal 2, so exactly 2 houses would have a soccer ball, or it could be 1, or it could even be 0. All of those would hold true for the phrase at most. I'd like you to pause the video and set up the distribution. You don't have to plug it in yet. Let's just set it up first, and then we'll plug it in to solve. Again, please pause the video, write out what you think you'd type into your calculator, then press play, and we'll enter it all in together. This time we have 3 formulas we're going to enter into our calculator. 6C2 times 0.41 squared times 0.59 to the 6 minus 2, which is 4 power. Does anybody notice that this kind of looks like our binomial expansion that we talked about in lesson 10.2? It looks very similar in setup. Okay, carrying on. It says or 1 house would have a soccer ball, so we're going to add 6C1 times 0.41 to the first power times 0.59 to the 6 minus 1, which is 5, plus then 6C0 for no houses having a soccer ball times 0.41 to the 0 times 0.59 to the 6th. All right, see if you can enter all of this in. The more you can do independently, the easier your homework is going to be. Pause the video and then see if you can type that all in, press play when you're done, and we'll see if we have a match. When you're finished, you should have 0.5236, which actually means you'd have a 52.36% chance, which is much higher than A or B. Here's a problem that's relating those free throw attempts we talked about earlier. Laura made exactly 85.5% of her free throw attempts last season. Determine the probability that she will make 10 of her next 16 free throw attempts. Our goal is to determine all of those key parts in that binomial expansion formula. We're going to attempt 16, that means n equals 16. It also asks us that we want to find the probability of making 10. That's what K would equal. Now the probability based on her past experience that Laura would make a free throw is 85.5% or 0.855. The complement to that, we just subtract from 1, and that would be 0.145. That's all the information we need. We're only going to do 1 round of this binomial experiment. NCK is 16C10 times the probability that she's successful, 0.855. We want 10 of those 16 free throws, and they can be made in any order. Doesn't have to be first, last, whatever. If we're going to make 10, we're going to miss 6 of them. So think about this before we enter this in. Do you think this is likely? If Laura makes 85.5% of her free throws on average, that's a pretty high probability she would make a free throw. So if she only makes 10 and misses 6, that seems not super likely. Let's validate that by plugging this in, and you should get 0.0155, which would indicate that's only a 1.55% chance that she makes exactly 10 out of 16. The last example that we'll talk about in the video lesson. A grocery store gives away scratch-off cards with a purchase of over $100, with a 30% chance of winning. Sophie has 5 scratch-off cards. What is the probability that she has 0 winners or 2 winners? What I'd like you to do is see if you can determine what N, K, P, whoops, there we go, hang on. Lost my pen here. There we go. And 1 minus P equal. Write that out and press play, and then we'll set it up from there. How did you do? N equals 5 because Sophie has 5 scratch-off tickets. But the probability we have no winners would mean K equals 0. Sad. The probability that any one of her tickets would be a winner is a 30% chance, or 0.3. That means the complement to that would be 0.7. So it's more likely she wouldn't have a winner than if she does have a winner. But let's determine the probability that there aren't any winners at all. We would plug in NCK, or 5C0. Now the probability that any one scratch-off card is a winner is 0.3, but we want none of those, which means all of the cards that Sophie has are not winners, 0.7 to the 5th. If you enter all of that in on your calculator at once, you would end up with 0.1681, or approximately 16.81% chance. Not super likely, so that's good. All right, last one. What is the probability that Sophie has exactly 2 winners of the 5 scratch-off cards that she has? That means K equals 2. That's the only change. The N, the P, the 1 minus P would all stay the same. The last thing we're going to enter in, 5C2 times 0.3 to the 2nd power for the 2 winners she hopefully has, times 0.7, that complement. If there are 2 winners, that means 5 minus 2, there'd be 3 scratch-off cards that aren't winners. All right, type that in. And the probability that Sophie would have exactly 2 winners is a little bit higher, 0.3087, which is approximately 30.87%. Now, don't scratch off those problems at the bottom. We'll cover those tomorrow in class.